Okay, so now we're going to talk about aircraft sheet metal structures. This is going to be our first class. We're going to We're going to start it off by just understanding the history of aircraft structures, the different types of structures that they are, names, and what you can expect to see out in the field. We're going to then move on to actually designing a sheet metal repair, where you'll learn how to rivet, and you'll learn how to do all that kind of artistry. From there, we'll talk a little bit about welding and just kind of like what is a weld, what are you looking for when you're inspecting a weld. Shocker, whenever welding actually comes up in the field, which is fairly rare, in my experience. You take it out to an actual welder who specializes in that, because there's a lot to it. Then from there, we're going to talk about the world of composites, and what you can expect to see in that. And that is the way that aviation is trending to. Most of the newer aircraft have at least some of their structure as composites, specifically carbon fiber. There's a lot of them that they are wholly carbon fiber, so you can expect to see a lot.
Okay, so we're not going to go through all of the history of aviation, like Otto Lilienthal and the slow progression from gliders to powered flight and all of that. If you're interested in that, we should have covered it in the general semester, and I'll put a link to that video below where you can see the history of aviation, and it's a pretty interesting history. But inside of that history, there's also a history of structures, and like how the aircraft steadily progressed from being made out of wood and fabric because it was light, to all of a sudden semi-monocoque structures that are made of metal, and then on into you get to the 70s and 80s, and people start experimenting with other types of composite structures like carbon fiber, and even producing the nearly all composite Cessna Citation Mustang and the 787, and all the aircraft now that are made strictly of, or nearly strictly of, carbon fiber. Now, the most common aircraft that you will see out in the wild is the fixed wing airplane. Now, the fixed wing airplane has come a long way. In this picture, you have a what's known as a tri wing, meaning tri meaning three, and then wing obviously meaning wing. Now, about the middle of World War I, they realized that, hey, that middle wing's not doing me a whole lot of good, and with a little bit of tweaks to the two wings that we have, we can get by with a lot lighter weight if we just simply get rid of that wing. So they went to a bi-wing airplane. Now the bi-wing definitely kind of took the day, at least for the rest of World War I, and all the way up into, I mean, they even get used in World War II, and in different places in for the rest of time. Nowadays, the bi-wing is pretty much relegated to nostalgia and maybe some acrobatic acts and things like that. They're not really commercially used anymore, but there for a long time, the bi-wing was the way to fly. Now, with some tweaks to the way the wing was designed, the way the rest of the airplane was designed for weight reduction, and some advanced engines, the mono wing came on the scene. Now, mono means one, and there's one wing, so a mono wing airplane. Now, this becomes the standard for the until today. I mean, we still produce mono wing airplanes even today. Now, on the future, you can expect to see a blended body. This is a design that takes the wings and it starts to try to use the fuselage of the airplane and produce enough lift so that way the whole airplane is helping the aircraft stay in the air, as opposed to just the wings doing all the work. Now, as you do this, you need less and less wing space because the body is also helping produce that amount of lift. Now, this design is nothing new. It's actually been around even since World War II. The Nazis were playing around with a big kind of flying V, and eventually we got the stealth bomber, the B-2 Spirit, and now the B-21 out of that same kind of thought train. But it's never really been able to to be employed commercially as of yet, but there are a lot of experimental aircraft out there, and this is definitely kind of the way things are looking for it in the future, just because it's so economical. You just don't need nearly as much power. The less power that you need, the less fuel you consume, and in the world of like sustainable aviation fuel and climate change narratives and all the good stuff, this a much more economical aircraft is definitely the way of the future. On top of that, fuel's just gotten really really expensive, and that's one of the key things that holds people back from being able to fly is just that it's too expensive. So if we were able to utilize better aircraft designs that just simply use less fuel, it's more likely that more people will fly, and you'll see growth in aviation that way. However, for now and for the immediacy of your career, this is what you're going to be working on: the standard run-of-the-mill airplane. Now, this is like a Cessna 172 that's been broken apart to kind of show you the different parts and pieces. I'm going to teach you the French French names for it, because you'll also hear that used widely in the industry. So the power plant, we're just going to start this graph and we'll work our way across from left to right. So the power plant is the fancy way to say aircraft engine. A power plant can be a turboprop, turbo shaft, a turbine engine of any variety, a reciprocating engine, even electric engines. Those are all power plants. Oftentimes, almost all the time, the propeller gets lumped into the power plant nomenclature as well. So whenever we study props, it'll be in power plant, because that's what goes on the in the end of an engine, effectively. But that's what that is. Landing gear, it's pretty self-explanatory. It's what the airplane lands on. There's nothing really special about that. From a structure standpoint, so let's back up. The power plant structure, you're going to have engine mounts, and that's going to be a tubular structure that we'll cover here in just a little bit. The landing gear, you can have a bunch of different types of landing gear. On a Cessna 172, you just simply have two, basically pieces of metal that come out that wheels are mounted to. But you can have all sorts of different types and different suspension systems that are lumped into that. From a structure standpoint, you're primarily they're typically solid pieces that you're not going to have to do a whole lot of work to. From the wings. This is when we're going to start kind of getting into what monocoque is and semi-monocoque is. So it's a good place to just kind of break that down. So a monocoque simply means that there is like one structure. The actual word is translated one shell as monocoque. Now, if you look on that bottom graphic, you have the skin. I'll say it's a stressed skin, and then you have formers, and that's just what helps hold the skin in its shape and its place. Are those formers, hence their name. Now, what's interesting about a monocoque structure is that it's a lot like a Coke can. This is always the way it was explained to me, and I always thought this was a good way to kind of remember it. They rely largely on the strength of the skin. That's why on the graphic there it says stressed skin. Thanks for our buddies over at Aviation Stack Exchange for providing that. Anyways, so if you think about it like a Coke can, if you have a Coke can that's not dented or anything, and it's empty, you can usually stand on it, all right? And that's because the skin is able to just like take that compression load and just hold it pretty effectively. The downside is that the moment that you compromise the skin in the slightest way, it loses a lot of its strength, if not all of its strength. So, like, you take that same Coke can and you dent it on the side, and you put the same body weight and you try to stand up on it, it's going to collapse down. That's the downside of a monocoque structure. The Coke can, your formers would be kind of like the ends, like the end of the Coke can, like where you drink out of, and then the bottom of it, and that helps form that skin that's going to carry the compression load of your body weight. So that's a monocoque structure. Now a semi-monocoque structure is the next one that is by far probably the most common aircraft structure out there. Now, if you notice on the graphic, the semi-monocoque structure and the monocoque structure look pretty much the same. There's still amount of stress that goes onto the skin. There's still formers. There's still bulkheads, but there's one key addition, and that is longerons. Now, longerons run the length of the aircraft, and they usually extend across several frame members to help the skin support the primary loads. They typically are made of aluminum, and or they're either a single piece or they're built up construction, depending on where they're at on the airplane and the type of airplane. But one of the things that I want you to take away from this is that the longerons are supplemented by other longitudinal members called stringers, because now this, whether or not they don't think they ever meant it this way, but this is how it eventually ended up becoming super relevant to just anybody, not just structures guys. Is that a lot of times this substructure of the airplane becomes almost like a grid pattern to find different places and different things on the aircraft. So you'll see guys say like, oh, look at like station 15 at stringer 1 or whatever. That means a very specific place on that aircraft. And so a lot of times these get named and numbered, and then will be referred to even in some jobs and things like that. But what the longerons and stringers do is they provide like another type of bracing that helps reinforce the skin. All right, now there's a lot of different types of structures, especially the more complicated you get. You get up into some of the more mature heavy commercial aircraft, and you'll see all manner of different substructures and reinforcements and things to keep the wing skin from tearing in case of an accident or a depressurization event, things like that. But at the end of the day, the heart of a metal airplane is its semi-monocoque construction with all those parts and pieces that you should know. Now, so those are the wings, and we're going to get a little bit more into the wings. But while we have this graphic up, we're going to talk about the fuselage. So fuselage, just like monocoque, semi-monocoque, they're all French words. Fuselage is also a French word, and so is empennage. Now, that empennage is not on here. This graphic has fuselage being pointed to from the cabin and to the what we would call like a tail boom or tail section of the airplane. The tail section of the airplane is almost always going to be referred to as the empennage. Now, as time goes on, I'm starting to see less and less reference to that. But if you ever see it, that just means that it's the aft section of the fuselage. And there's always kind of a debate of where it begins and where it ends. Unless you got something like a Technum or a Bell 206 that has a very 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 precise transition point where there's no mistaking where it stops being the fuselage and starts being the empennage. But know that's there. You also have flight controls. That's you should be pretty familiar with that at this point. And we're gonna have like a whole rigging class. We're talking like a lot about flight controls, and then there's another thing on there that'll say stabilizers. Now you have a vertical stabilizer and a horizontal stabilizer. Now in construction for structures, types of just discussion, those are very much like wings. They're not really going to be that different. The primary thing to remember of these is that they're there to help streamline the airplane, help keep it tracking correctly, and they don't move. They're unless you have like a stabilator, and we'll get into that in our rigging class. Where you can have the stabilizer move, but for the most part, a true blue stabilizer is not going to move or go anywhere. It just becomes the mounting points for other. Okay, so let's talk about the different types of wings. We're going to look at it from kind of an overhead view to give you those different types, and then we're going to look at it from straight on view to talk about dihedral and stuff, things like that. All right, so the top left you have a tapered leading edge. So notice that like it gets a little bit more, I guess, aggressive. It kind of gets bigger the closer you get into the cockpit, and then a straight trailing edge. So it's just a straight line across the back. Now this will a variety. There's a couple of them that we're going to talk about here. That's just a rectangular wing. Now rectangular wings are really good for going low and slow, and that's what that type of aircraft is going to be doing. It's not a high performance aircraft. It's going to be built for economical lift production and stability, and that's really kind of all there is to it. The next one's going to be tapered leading edges and trailing edges. So both the leading edge and the trailing edge have been tapered off. Likely, that's going to give it. You're going to have the ability to generate a lot of lift because the wing footprint is pretty big at lower air speeds, but still be kind of nimble and fast because those tapers will allow it to do it. This is not a wing design that you generally see out there. That's definitely was kind of a thing probably like mid of the last century, but like not a whole lot of airplanes embraced it. And for obvious reasons, it's kind of an awkward design, has problems. Kind of a rule you'll hear like aircraft designers talk about that if it looks pretty, it is pretty. Like airplanes that look really good and are aesthetically pleasing generally fly better. Whereas the ones that look kind of awkward and you're like, what is going on there? Those are going to be the ones that kind of you end up having problems with. All right, so on the right you have the delta wing. So the delta wing is really good for high speed. Now there's disadvantages to it that like at lower speeds it doesn't produce as much lift. So you basically always have to be kind of like leaning forward on the throttle, and so like your Mirages and things like that will use those types of wings. Your sweepback wings, that's an F-16 on the bottom left. Those wings, notice that they're small, but the F-16 is basically a rocket ship. There's a huge engine that the pilot just sits in front of, and the wings there, while they generate lift, you don't need that much wing out there because the lifting surface is going so much faster. So there's kind of like an efficiency factor. So if you look at like a Predator drone, very small engine but humongous wings. Okay, an F-16, very big engine, small wings. So like that's just simply because like for every square inch of the F-16's wings, it's able to generate way more lift than a normal airplane because that engine is pushing the airplane through the air that much faster. The advantage those wings also give it is allows it to be nimble. So it can do snap rolls, whereas the airplane above it on the graphic and to its right won't do that. Like they'll still roll, but they're going to roll a lot slower because they have to push that big wing through the air with a lot less power on the engine. Anyway, so next one is like a straight leading and trailing edges. This will be known as like the Hershey bar wing. You'll see that a lot of times in Piper Cherokees is the one that like kind of really is kind of known for the Hershey bar wing. But that just basically means it's a big rectangle. There's nothing really wrong with it. There's definitely disadvantages to having that. It could be more productive with a couple of minor tweaks to it, and that's why it kind of has that designated the Hershey bar wing. As Piper kind of progressed on with the Cherokee, they had different iterations of those wings come out, and they got away from the kind of Hershey bar design. And the one that you see to the right is you have a straight leading edge with a tapered trailing edge. That's kind of like your Cherokee Warriors and things like that. Where and there's multiple like sub models of the Cherokee. But anyways, the whole so what of that is to be able to produce more lift, the same amount of wing without trying to add a whole lot of weight or change the power plant. And with just a few design tweaks, they were able to accomplish that. And so the thing to take away from this is that like every single wing is on a structure standpoint, they're built exactly the same. And so what ends up happening is you take that structure skill set and you apply it to the mission that plane has, and you make it work. Now, if you were to take the wings off of the F-16 and then put it on the Cherokee or vice versa, they'd be terrible airplanes. They wouldn't do what you wanted them to do. You'd probably end up just basically like crashing or never even get off the ground to start with. All right, so the different wing designs can also be modified if you look at them not from the top down but just directly on. You have low wings, high wings, gull wings, inverted gull wings, mid wings, and dihedral. So the vast majority of your aircraft, like all your jets, are going to be low wings because they're more efficient for the mission that they're trying to accomplish. High wing aircraft, they allow you to look down. They allow it to fly slower because it's going to take a less like substructure to be able to attach it and all that good stuff. And so like it's just a more efficient wing. So a lot of your trainers will be that way. Your gull wing and inverted gull wings. The one that I know pretty well is the Corsair, the F4 from World War II. They used an inverted gull wing. Same thing with the F4 from Vietnam. They used inverted gull wings because it allows the wing doesn't stop producing lift in those angles on the wing. But it allows them to take up less space, like on a carrier deck. However, they're not. It's not optimal. You're always giving up something. Anything in engineering is always a kind of a balancing act between like, okay, what about this can we give up to gain maybe a little bit over here where we want to get some. The mid wing went away. I've never seen a new airplane produce the mid wing. And that's simply because the high wing and the low wing do such a good job at their various missions, and you need to basically choose what the mission of the plane is going to be and then build it for that. The mid wing was trying to I guess like stand with 1 foot in both camps and didn't work very well. Wing dehedral that also like so on this it has like dehedral as a type of wing. It's more of a attribute of wings. So most wings have some degree of dehedral built into it. And dehedral, all it is that the angle of the wings in which the wings are canted up. Usually, you have a couple of degrees. It allows for the aircraft to fly better, more efficiently, and things that are just kind of like beyond what we're here to talk about, so we won't get too far into it. But just know that dehedral is not necessarily a type of wing as much as it is a attribute of wings. So another way that wings have progressed is to become a full cantilever wing. Now, old biplanes had all this bracing that you see on the far right hand side, but as time went on, designs were refined to eventually you get to the full cantilever wing. Now, there is amount of like long struts that are braced that still happen out there in the wide world. So you think of like your Piper Cubs, your Aviat Huskies, your Cessna aircraft. They still have struts that brace the wing that help attach it. But by and large, almost all aircraft are full cantilever now. You don't really have to worry about those. But that's something if you ever see it referred to, that's what the maintenance manual is talking about. Okay, so the interior of the wing is something that we need to talk about before we really kind of like dive too far into any other type of construction. Um, there's different nomenclature for the different structures that you see inside of the wing, and this nomenclature is very important to know because it's going to be referred to on a regular basis. Sometimes even very specifically. So like if they say stringer number 2, then they're talking about a very specific stringer. All right, so there are the core of any wing to get us started is the spar. All right, now depending on the aircraft design, it could have a spar or it could have multiple spars. It really just kind of depends on which aircraft we're talking about and what its mission is, what its wing design is, all that kind of stuff. Now, on the graphic you see on the left, you have a rear spar and a front spar. So you effectively they've built like a little box, like a little Hershey bar wing. But some aircraft they have a single spar and everything else connects to that spar, and that's how the wing is designed. Some of them have multiple spars. It really just depends. Now the definition of a spar is it's going to run from the wingtip to the fuselage, and many times through the fuselage into the other wing. But that's what the spar does. Now the ribs are just like ribs. They give structure to the skin of the wing. So like when you look at a wing and it's kind of like got this nice, pretty camber where it curves on top and all that good stuff. What you're seeing is evidence of the ribs. The ribs attach to the spars. They run in between the spars if there's two of them. Sometimes the spars go through the ribs, but either way, the ribs are really what gives the wing its shape and structure. The spars are what give the wing its strength for the most part. Now, those ribs, then you can have other ribs. This one is showing what a nose rib looks like. Those are just little pieces of sheet metal to kind of give the leading edge some shape. On the graphic on your right, you have the stringers that run up and down the wing with the spars, but these are not super thick and hold the strength of the wing. It just helps kind of connect the ribs, keep them straight, and keep them structurally sound. And then the skin then attaches on top of that. So when you look at a plane and you see a bunch of rivets, what you're seeing are the rivets that are drilled into the skin, or through the skin and into the stringers or into the ribs to attach them. So the kind of basic kind of construction is the stringer or the the spar, then the ribs attached to the spar. The stringers then attach to the ribs to give it like kind of this structure. And at this point, the house is like framed, and the last step is to attach the skin via rivets onto it. Now, if you do any kind of kit building or you're interested in kit building, you can see that this whole process go together really fast by simply just like watching some of these guys just do layups and just sit there and rivet skin onto that substructure like that. But this is the kind of the base structure that the entire airplane is going to follow. All right, here's some examples of what spars can look like. So the one on the left is probably the most common that you're going to find. Those circular holes that are cut out of that I-beam like structure are called lighting holes. They literally just like make the aircraft lighter. It doesn't really compromise that much of the structural integrity, but the weight savings is pretty substantial. So it's a very common and popular design. The other ones you'll see in different places. The more robust, very structurally sound ones that you'll see like kind of off on the right, those are ones you'll see on like heavy commercial aviation. So if you go and look inside of like a 737 Max's structure, you're going to see that type of wing spar. Whereas if you go and look at a Cessna 172 or a Piper Cherokee or something really lightweight, you're definitely going to see more of the one on the far left. The other three that are in the middle you can find elsewhere. It just really kind of depends on what the aircraft is, what its mission is, what its wing design is, all those types of things. But those are different spar types. Here's a graphic that's a little bit up close and personal of what a heavy commercial wing spar is going to look like. This is a plate web spring spar with vertical stiffeners. Those stiffeners run up and down the length of the spar, well, the height of the spar, and basically give it a little bit stronger construction without adding too much more weight. You can kind of study that and get an idea of what a spar will look like. Now, for the most part, you'll never really have to mess with this. For the most part, whenever a spar is laid up and everything's attached to it, and it just gets kind of buried and lost and confused. The only time you're ever going to mess with this is if you start modding aircraft or if one's crashed and you're trying to restore it. Every once in a while you'll have a random AD, like on my Cherokee we have to do a eddy current inspection on the spar. That's something that comes up, but for the most part the spars are kind of out of sight, out of mind. Okay, we won't spend just a whole lot of time on this, but I do want to show you what the structures of a 737 kind of looks like. If you look, there's a couple of interesting things that you'll see that you won't see at other places. So, like the aft pressure bulkhead, that's a significant structural component of most heavy commercial aircraft. The 737, you get in there, it's a huge dome. It's about as tall as you are, so that's something to kind of take away from. Notice the amount of stringers that are in there, and you also have floor beams because the cargo area is underneath where the people sit. Even on freighters, then they put the cargo area up top. You'll still have this blank space underneath, and that's just simply because, like, in order to make it structurally sound and be able to pressurize, it creates more space space than it can actually be used. If you were to fill it all up with, say, like water for a tanker or something, the aircraft would never be able to get off the ground. But this kind of breaks things down and shows you the construction of a 737. Okay, this shows you kind of the wing construction that you have there. Notice that you have like fuel tanks, surge fuel tanks that are mounted on the middle, and then you have the center fuel tank, and then all the different flight controls that are mounted on the kind of the perimeter of the wing. But notice the ribs, and you can start to see why they're used as a way to kind of locate things. Like so, if you have some sort of structures damage, you might call out a rib in the write up. It's just like, hey, look, there's damage next to rib number 24 or whatever. Also notice the complexity of the flight controls. You have flaps, slats, you have inboard, outboard flaps. You have spoilers, outboard ground spoilers, ailerons, all kinds of things, and then this winglet on there. And what the winglet does is it prevents the wingtip vortices from progressing inward on the wing and spoiling the lift and creating disrupted flow anywhere on the wing. You want laminar flow at all flight stages, and those winglets, whenever the airplane is at like a high angle of attack, low airspeed, high power setting, those vortices are really kind of like cranking up. It helps the wing produce more lift and therefore makes it safer. And then it also creates moves the vortices away from the wing in flight to help it save significant amounts of fuel. Okay, and this is the inner workings of the horizontal stabilizer and the vertical stabilizer. Notice there's a center truss section that kind of looks like a pentagram almost, and then you have the same concept. There's spars and there's ribs that give those stabilizers shape. There's nothing really super special or different than the wing, other than there's less going on there, and then they're mounted to the side and top of the fuselage to give that that stability on the empennage, the tail section. Okay, so if we're going to be good sheet metal mechanics or people that are capable of repairing aircraft as needed, we need to kind of build our understanding. Now we understand how like how sheet metal is used in structures and with the base kind of structure that we're going to be expected to be able to repair. Let's talk about like the metal itself, and then we're going to go through the aluminum. We're going to kind of recap from general. Once again, we'll put the metalworking link in the description, so that way you can go back and review it if you get super lost. But we're going to start talking about like the type of metal that we actually use, and it's most of the time, almost all the time, it's going to be 1100 aluminum. All right, now you can get whenever you say like the 1100 alloy, that's just simply saying that it's commercially pure aluminum. All right, it's aircraft grade, ready to go, all that good stuff. But it's going to come in different forms. So like what you have in front of you is like the different forms that you can get aluminum. Like if you were to call up 1-800-aluminum and order it, you could get sheet aluminum. That's going to be the most common type of metal that you'll work with. If you're having to repair a wing or whatever, the sheet metal is what you're going to get. A lot of times, like the structural repair manual is going to call out and say like, hey, look, you need to have like 20,000 aluminum of like 2024 T3 or whatever the thing is, and that's the way it's going to show up whenever you order it from like Granger or whoever. That's what you're going to get. But you can also get plate aluminum. But obviously plates are plates. They're thick, heavy pieces of aluminum, so it goes without saying that we don't use that much of it. But there are places where you might see aluminum plates being used. Extrusions. There is definitely a place for extrusions on the aircraft and different structures, depending on what aircraft you're working on. That'll be the case. I've never seen bar aluminum ever used on aircraft a lot, except for in manufacturing. You might get bar aluminum that gets then machined down to a certain type of part or whatever. So if you get into the manufacturing world, you might be able to see bar aluminum. And then you have like pipe and round tube. We're going to use a lot of that. In general, you had to deal with aluminum pipe to create your flareless fittings or your flared fittings, and that sort of thing. So that's something that will be around for the rest of your career. Now, in our previous discussions about metal, we talked about how alloys help add certain characteristics to the aluminum that we're working with, but that's not necessarily the only way to get the characteristics that we want. We can also harden them or soften them or do different things to aluminum via heat to actually get a desired end state for that metal, so that way we can use it as needed. All right, the most widely used alloys in aircraft constructions are hardened by heat treatment rather than cold work. These alloys are designated by somewhat different sets of symbols. T4 through W indicate solution heated heat treatment and quenched, but they're not aged. And the T6 indicates the alloy in the heat treated hardened condition. And all of the different W to T10 numbers will tell you a little bit about what that hardening process looked like for that in particular piece of metal. Where you're going to see this probably the most prominently is in the structural repair manual. Whenever you say like, hey, look, there's a hole in this airplane, so we're going to cut the hole out and we're going to put a patch on there. What metal do we need to order to get this repair going? And then you'll get in the structural repair manual. It'll say it's 2024 T4 or whatever, and that's where you're really going to want to pay attention. But just so that way you can be a competent mechanic, you can know a little bit about that aluminum by simply taking those T numbers and breaking them down. Now, aluminum alloy sheets are marked with the specification number on approximately every square foot of material. Now, if it's not marked, and this is important, if it's not marked, don't use it. Even if you're like 90% sure that this is what the metal is, don't use it, because there is not really a perceptible way for you as the mechanic to tell apart some of these nuanced pieces of metal. If it's 40 thousandths aluminum, but one is a T10, the other one is a T4, you may not be able to tell them apart. And so, like, it's just a good practice that, like, if I cannot see what's stamped by the manufacturer on this metal, then we're not going to mess with it. If for any reason this identification is not on the material, it is possible to separate heat-treated alloys from non-heat treatable alloys by immersing the sample material in a 10% solution of caustic soda. The heat-treatable alloys turn black due to the copper content, whereas the other remain bright. In the case of clad metal, the surface remains bright, but there is a dark area in the middle when viewed from the edge. Alright, so that's out of the 8083. There is a way to start to tell these apart. I'm telling you, just as a aircraft owner, mechanic, and pilot, don't do that. Like, it's just bite the bullet, order the metal that you need, and then take the rest to the scrapyard or sell it to somebody with a little bit less standards. Just have it, and that just goes for anything in aviation. There's going to be the published set minimum standard for everything. I don't care if it's how many feet clear of clouds from your airplane for a VFR flight, or the type of aluminum that you're going to use on the airplane. There's always those set standards. You'll have to develop your own what they call personal minimums. My personal minimum for sheet metal is that, like, I'm not smart enough to be able to definitively tell apart the two, so I'm just going to defer away from using anything except for the stuff that is very clearly marked. Okay, so let's talk about alcad aluminum. So you have the terms alcad and pureclad are used to designate sheets that consist of aluminum alloy core coated with a layer of pure aluminum to the depth of approximately 5.5% on each side. The pure aluminum coating affords dual protection for the core, preventing contact with any corrosive agents and protecting the core electrolytically by preventing any attack caused by scratching or from other abrasions. So it's really important, and alcad gets used a lot on aircraft. Because like whenever you go to install it, you'll find that like your drill may wander and scratch the surface, or just simply moving it from point A to point B. The banding that's around the aluminum whenever you unpack it might have scratched it. And whenever you have like regular aluminum that's just pure aluminum and gets scratched like that, you open up for all kinds of problems, especially with alloys. You get like intergranular corrosion, or you can have just any sort of corrosive attack start right there at that scratch. Well, Alcad effectively gives a sacrificial layer of that pure aluminum to kind of like the corrosion elements that are out there, and stops it before it really kind of penetrates deeper into the alloy before where you actually really need the strength. Okay, so what is the process for heat treating aluminum? So there's four distinct steps. First off is that you have to heat it to a temperature that you want to get it to, and that's important. That temperature is important because different temperatures will result in different hardenings and other, characteristics of the aluminum as it cools down. Secondly, then soaking at temperature for a specified length of time. And you're going to see this in composites whenever we get there as well. It's not just that you get it that hot, but it also you get it that hot and it stays that hot for a certain period of time. So you could get it to like say 100 degrees for 3 days and it might result in this type of hardening. Or you might be able to get it to 1,000 degrees for 3 minutes and you get the same type of hardening or maybe something that's radically different. And so that soak time is really, really important. Then you have to rapidly quench it to a relatively low temperature. If you're reading some of the structural repair manuals, it'll say heat it for like 8 hours, but then you have like 8 seconds to quench it. So that means that you take it right out of the oven, it goes right into whatever you're quenching it in to cause that rapid loss of heat, which causes the metal to set up in a certain type of hardness. And then lastly, aging or precipitation hardening either by spontaneously at room temperature or because of a low temperature thermal treatment. So that means that like you just take it and you set it up on a shelf and it just sits there, and as it cools, that metal goes through a change on the inside of it that causes it to harden up to a certain degree. Or you might want to put it into some sort of like low temperature, like throw it in a refrigerator or something like that, and it'll cause it to set up faster. But anyways, those are the four steps. So heat it, soak it, quench it, and then age it. Like those four steps for heat treating aluminum or really any kind of metal. Okay, so let's talk a little bit about annealing. Now, the part that's being annealed here in the picture is actually steel, but it was too cool of a picture not to use here. But anyways, the annealing procedure for aluminum alloys consists of heating the alloys to an elevated temperature and holding or soaking them at this temperature for a length of time, depending on the mass of the metal, and then cooling it in still air. So, I mean, not quenching it and not letting it or not subjecting to any sort of thermal treatment, but just simply like taking it off and just setting it on the shelf and letting it cool off. Annealing leaves the metal in its best condition for cold working. However, when the prolonged forming operations are involved, the metal takes on a condition known as mechanical hardness and resists further working. So once it's annealed, the only way to really kind of like undo it is just melt it down and start all over again. It may be necessary to anneal a part several times during the forming process to avoid cracking. Now that's serious because when you get so hot, like the metal is going to want to expand, and sometimes it expands beyond its own capabilities and causes a crack. So what you'll do is like you'll slowly step it up over time, so that way it keeps it gets hot and let it sit there for a while, then gets a little bit hotter and then let it sit there for a while, and so rather than shock, you always hear about shock cooling with engines. You don't want to shock heat the metal either. Aluminum alloys should not be used in an annealed state for parts and fittings. Clad parts should be heated as quickly as carefully as possible, since long exposure to heat tends to cause some of the constituents of the core to diffuse into cladding. This reduces the corrosion resistance of the cladding. So that's a long way to say, like, make sure that you're treating the metal that you're annealing. If you ever find yourself annealing aluminum, which is going to be rare, make sure that you're doing it correctly, or else it could have an adverse effect. Okay, so it's kind of unlikely that you'll get into needing to heat treat your own metal or anything else like that. There are some times where that will come out. One place that you will see this is heat treating certain types of rivets. I can remember going into a stall at Boeing years ago, and in there was like a little refrigerator with a bunch of trays of rivets on there because they were doing some rework to a plane, and they had to heat treat these rivets and then immediately like put them in a refrigerator to get them to the right hardness before they installed them. And then you have other things. I mean, like whereas the cold will cause metal to condense. Sometimes they'll put them in these refrigerators, cause the rivet to draw up, and then they'll slide them in, and then drive the rivet. And then as the rivet warms up, it also helps seat in there to into the hole that it was put into. So you'll see these types of applications a lot more readily than you will see like having to like quench your own aluminum or anything like that. Most of that's just you just simply order it, but it's a good skill set to have in case you can't get a hold of a certain type of metal or anything. This is a like what you're looking at now is just a homemade oven. You just kind of pulled it off YouTube, but like because they like a lot of these guys that do this type of work, that's what they'll end up doing. You used to be able to order them. You might still be able to find a vendor that will sell them, but for the most part, and this goes with composites as well, is that like it's just far easier to just build your own. They're not really that expensive, not necessarily that hard. And with some plans or just some little know-how, you kind of put it together and get it to where you want to go. But I just wanted to show you this because like this is an area where you will run into heat treating of metals. But even though it's kind of on occasion, and a lot of times these types of rivets, the only times that you're actually having to heat treat rivets and then put them in the metal is whenever you're dealing with big heavy structures. For the most part, but yeah, so that's heat treating rivets. Okay, so let's talk about sheet metal defects. These are defects that you can either get from the sheet metal whenever it just arrives to your shop, or that you can induce. The first one is burrs. So, like whenever we are working in the shop, one of the steps that you're gonna go through on your projects is to deburr the hole that you made. Now, what is deburring? So, all whenever you drill or you cut. Any sort of aluminum, a lot of times there's going to be these little flakes that form around the edges of the hole, and so deburring effectively just removes the burr from the edge. So it's going to cut it off with the deburring tool, and a lot of times you're going to come by with some sort of abrasive cloth and then smooth it out on that. Be it like Scotch Brite's usually probably the best one. It's not the most aggressive, so it makes this very nice, gentle, rounded hole like you kind of see on the right picture that we're looking at. So that is burrs. Okay, so corrosion's another one that you'll get. This one is more common than the others. Generally, like the people that are selling sheet metal manage to get all the burrs off, but corrosion can happen anywhere along the way. If they've treated the metal right, then and it's been protected, then you shouldn't have this issue. However, at your shop or at work, you can easily see corrosion start to build up. That's something you want to be really cognizant of the way you store excess sheet metal for future projects, and you want to make sure that before you install any metal on the aircraft you're using for repairs, that you screen it for corrosion, because that's the last thing you want to do is put a problem on an airplane. You want to stop the problems rather than do that. Okay, so cracks are another one that will show up. You'll get these in sheet metal from time to time. It's once again, it's kind of rare because usually they're trying to ship quality products. However, whenever you're doing sheet metal inspections or doing any kind of structures inspections, this is like the number one thing you're looking for. They'll say it's corrosion and stuff, and yeah, sure, corrosion, you want to look for it, but corrosion is usually pretty obvious. Cracks, on the other hand, cracks can persist for years and you'll never see them, but they are extremely dangerous. If you remember back in general, I told a story about finding a crack in on the tail rotor gearbox mounts on the OH-58 one day in Baghdad. We grabbed it's just a kind of a process. We'd always grab the tail rotor gearbox drive shaft and lift up on it, because if anything was cracked, it would move. And I picked up on this one, and it moved at a pretty good distance. And so this is something you want to pay attention to. This is also what a lot of your NDI inspections are going to come looking for. They're looking for cracks inside of metal, just because over time the stress and strain of flight will weigh on them, and the cracks will start to form. Okay, cuts are another thing that will happen to sheet metal. What ends up happening is you have a brand new like 4x4 piece of 2024 that you're going to cut out a piece to work with. Well, as you cut, you scratch things, or maybe it like rubs up against the box brake or whatever the situation is, but it gouges the metal, and it might be ever so slightly. But then you take that same piece of sheet metal and you put it back up on the rack, and it sits for a year. Then you come back and get it again. Well, it's had for a year exposed to the elements, that inner workings of the sheet. And so now you're going to take that same piece of sheet metal, make another repair out of it, and then put it on an aircraft. What you've done is you've just introduced potential corrosion onto the airplane. So one of the things that you want to be really careful about is inducing cuts into sheet metal. Now sometimes you'll get them, and there might have been something happen in shipping. It'll be cut. And the best thing is just send it back and get a new piece of metal and call it a day. But uh, the way to prevent accidentally scratching or cutting or doing anything like that is to mask off what you're not going to use. Like use some tape or butcher block paper or something to just keep it protected, so that way you don't accidentally gouge it. But cuts are another sheet metal defect that you should be aware of. Okay, some other common types of damage that we could run into is just real simple type things like dents. Like you can see this wing's all dented up in the top left hand corner. It's just an indentation in the metal surface produced by an object striking it with force. It's really simple, just like denting your car door or anything else like that. Gouges are often come with the dent. I mean, if something hit it to dent it, usually it's going to gouge the metal. Anytime that you compromise the surface of the metal through any means necessary, that you have a corrosion issue that you need to deal with and protect it from. So you need to remove any corrosion that's there, retreat the sheet metal, and then kind of build it up back to its original state, which we'll get into in the next class. We're going to talk about like sheet metal repairs and kind of the basics that come with it. Other things like nicks, pitting, scratches, scores, even stains, depending on. I mean, if you have like another airplane that's like red in color and it hits this light blue airplane, it's going to impregnate that red paint into it. That's another type of sheet metal damage or a defect that could potentially happen. Most of this is going to happen out in the field. You're not usually going to get regular run-of-the-mill sheet metal that has this sort of damage to it. But no matter what you do, always look over the sheet metal that you're about to put on the aircraft, because there are always these manufacturer defects that happen. It may have come out of the factory and been just perfectly fine, but the guy that's shipping it might have dropped something on it. Something could have got stacked on it. Who knows? What. Yeah, and so what you want to do is unpack the whole thing, look at it, make sure that it's everything's correct before you accept it, and then go from there.
Okay, so when we talk about inspecting metal structures, you're going to have two basic camps of inspections. The most common one is going to be the general visual inspection. That means simply like looking. The best way to look for damage to an aircraft is simply to clean it. One of the best tools that you could ever use that a lot of people don't ever think about is the shop towel. You turn around and just wipe everything down, get all the dirt off, get all the grease off, and remove anything that could potentially be hiding some sort of corrosion, a crack, some sort of damage on there. If you see anything that looks suspicious or some area that's hard to get into, a jeweler's loop is always going to be in your toolbox. Take it, you're going to come down there and you're just going to like magnify the area that looks like it needs to be inspected. And simply just hold it back and see what's going on there. If it is a crack, you'll see it. All right. The next step that you want to do to inspect cracks or any sort of like damage that could just be superficial is simply take your thumbnail, rake it over the top. If it'll catch your thumbnail, then it's something that needs to be investigated. Now, once you've determined that you have damage that's not just some superficial thing that you can paint over and go about your merry way, that it's actual like crack, it's an actual serious scratch or something like that, you need to know to what extent that damage actually has gone into the aircraft structure. That's when you bring in your non-destructive testing or non-destructive inspection team, or you do it yourself. That could be a dye penetrant inspection, and for most of your GA applications that seems to suffice. Or you could have to get a eddy current machine, or ultrasonic, or depending on what kind of structure it is and what the structural repair manual calls for inspecting that particular item. Once you have those systems brought to bear on the situation, you can make a determination of what the next step is. From there, you're going to turn around and say, like, hey, what limits, damage limits are allowed per the maintenance manual, be it the structural repair manual or the AMM, depending on the aircraft manufacturer. You make that determination, then you proceed on. And that'll lead us into our next class, where we're actually going to design repairs, and we're going to execute those repairs that we designed. So now let's move on to that.